Hi, and a very good day, everyone. Let me introduce myself first. I'm Shashikumar from Tribank S5 and one of the representatives from Group 1 of Communication Principle Assignment. Today, I would like to present our MATLAB simulation work, which is to design and perform a wireless communication system using DPSK, Differential Phase Shift Keying Modulation Technique, along with my another group member, Arvind. Let's go. First of all, what is MATLAB? MATLAB is an abbreviation of Matrix Laboratory, which is a proprietary multi-paradigm programming language and numeric computing environment developed by MathWorks. MATLAB allows matrix manipulations, plotting of functions and data, implementation of algorithms, creation of user interfaces, and interfacing with programs written in other languages too. Although MATLAB is intended primarily for numeric computing, an optional toolbox uses the MUPAD symbolic engine, allowing access to symbolic computing abilities. An additional package, Simulink, adds graphical multi-domain simulation and model-based design for dynamic and embedded systems. Besides, Simulink is a MATLAB-based graphical programming environment for modeling, simulating, and analyzing multi-domain dynamical systems. Its primary interface is a graphical block diagramming tool and a customizable set of block libraries. It offers tight integration with the rest of the MATLAB environment and can either drive MATLAB or be scripted from it. Simulink is widely used in automatic control and digital signal processing for multi-domain simulation and model-based design. Therefore, this MATLAB Simulink feature has been utilized to complete this project successfully through simulation. Let's take a look at those simulations. Well, this is the Simulink model that has been designed for this project by using several blocks. Firstly is the random integer generator block, which will generate a random input as the message signal. Next is the DBPSK block, also known as Differential Binary Phase Shift Keying block, to modulate the message signal with carrier signal. This modulation process will occur by serial binary data from random integer block passed through XNOR gate, and the output is fed back via 1-bit delay. The resulting bit stream is applied to the balance modulator to produce DPSK signal. Apart from that, complex to real imaginary converter block was used in this project design due to the complex modulated output waveform which was produced by the DPPSK block is unreadable by the user. Thus, this block will separate the real and imaginary part of the complex output waveform and multiply it by sine wave respectively. Then these two output waveforms will be combined together to produce a readable and modulated output waveform. Now, I would like to hand over this presentation to my fellow group member Arvind. Thank you.
Now I will discuss on AWGN block. What is AWGN block? AWGN block is an additive white Gaussian noise used to add white Gaussian noise to the modulated signal that passes through the and imitates various random processes seen in nature from the Simulink model. Then it will go to the constellation diagram. What is the function of constellation diagram? The function of constellation diagram is to ensure whether the modulation process is working properly or not. For instance, if simulation runs for 10 seconds, there will be 10 dots will be shown on the constellation diagram. If the number of dots fail to tally with the duration of simulation, then the modulation process is not working properly. Subsequently, the AWGN output will be sent to the demodulation block of DPSK to retrieve the initial message signal without any errors. In DPSK demodulation block, DPSK signal will pass to the balance modulator and 1-bit delay circuit. The resulting signal is passed to the LPF, which produces binary data. This passes to comparator circuit or schematic trigger circuit to produce clean and high speed binary levels. Finally, all of these output waveforms will be shown to the user with the aid of the scope block in MATLAB Simulink model. Before we run the simulation, we need to set the values for each block. For instance, for random integer block, we need to set the set size as a 2 that's stated in our assignment. For DBPSK, the mth array number will follow the set size, and the input type is integer, constellation ordering is a binary, and phase rotation is a pi, and output data type is a double. For AWGN, there is no need to change the values. For DBPSK, the values will follow as the modulation DBPSK. So M array number is 2, output type is integer, constellation ordering is binary, phase rotation is pi, and output data type is double. For the complex to real imaginary converter, we need sine waveform and cos waveform. So therefore we will be using sine wave generator for these two. For sine wave, we just set the amplitude as a 4, frequency 8 times pi, and the sample time is 0.001. Whereas for cos wave generator, we set amplitude, frequency as a 8 pi, and phase is pi over 2 to obtain cos waveform. And then we need to set the constellation diagram. Go to setting, change the symbol to display as a user defined, and change to 1000. And run the simulation. As you can see here, the constellation diagram have a 10 dots, which runs for 10 seconds. This shows that the modulation and demodulation process occurred perfectly. This is the input waveform and modulation waveform. Whenever the input waveform reaches the zeros, there will be a phase shift. As you can see here, when the input waveform reaches 0, there will be phase shifted, and here too. So as you can see, there will be 1, 2, 3. There will be 3 phase shift because there is 3 zeros in input waveform. The output of demodulation waveform is exactly same as input waveform. This shows that demodulation process occurred correctly. This is all the simulation for the DPSK. That's all from us. Thank you.